who's talking about relativistic quantum communication. And please.
Okay, thank you. Thank you very much for the organizers for the invitation. Gabriel have asked me to talk a little bit about the work I've been doing in the last few years on relativistic quantum communication. So I'm going to say a few words about it. Well, in the last few years, last few decades, actually, there have been shown to be a very deep connection between gravity, quantum field theory or quantum mechanics, and quantum information theory in general. And this relation, this interplay between those fields traces back to first to the so-called black hole thermodynamics, right? To the black hole thermodynamics, which is basically when says that when one considers quantum effects, when one takes quantum effects into consideration, we have that the black hole mechanical laws are basically the laws of thermodynamics applied to black holes. So black holes have a very well-defined temperature, which is proportional, for instance, for a spherical black hole to the inverse of its mass. They have a well-defined entropy, which is proportional to its area of the event horizon. And they satisfy all the laws of thermodynamics. In particular, they satisfy the generalized second law, which states that when considered black hole and matter fields outside the black hole, the total entropy of the black hole plus the matter fields never decreases, right? Which has this generalized second law has been proven in very general context today, up to date. However, although this relation, the thermodynamic of black holes makes understand more deeply the relation between gravity and quantum mechanics and thermodynamics, it raises several new questions, which we're still trying to address. The first one is basically black holes are completely described by their mass, angular momentum, and charge. However, they have only 3 parameters to describe a huge amount of entropy given by this area law here. So the first question we're still trying to answer is, what's the origin of this black hole entropy, right? The second question concerns the fate of the information that has fallen into the black hole. So we have the collapse of a star, which forms a black hole. It emits Hawking radiation, so we have information that has fallen into the black hole of the matter fields, the quantum fields, the star, etc., that enter the black holes and end up in the singularity. As the black holes emit Hawking radiation, its energy comes from somewhere. And the only place it can come is the mass of the black hole. So as it emits radiation to infinity, it loses mass. If it loses mass, it gets hotter and emits more and more energetical particles. So it can eventually evaporate completely and disappear in a final event. And then what happens is that all the information that has fallen to the black hole ends up in the singularity, and the information gets destroyed in the singularity. So in the usual analysis, the usual semi-classical analysis on considers is given by this classical Penrose diagram for the evaporation process, which is a non-global hyperbolic spacetime, right? So you have initial pure states here describing the matter fields, the star, evolving, and the final state here after the evaporation of the black hole to a mixed state, which is a pure thermal state. Of course, this is not a actually a paradox because we have an open system here. The singularity opens up our quantum system here. So we have an open quantum system, and the evolution need not to be a unitary evolution. If you want consider not only this time slice here, but what also the singularity, one has all the information initially contained in this state. All right. However, this is only one possibility for the evaporation process. For instance, in collaboration with Matzas, Pegas, which is his PhD student, and Daniel Vanzella, we have considered a completely global hyperbolic description of the evaporation process in this recent paper here. However, the question remains, what's the fate of the information that has fallen into the black hole? It's possible that due to some subtle effects due to gravity and quantum gravity degrees of freedom, one can change the correlations between the modes that enter and the modes that are emitted to infinity in such a way that information can come back to observers that always remain outside the black hole. That's an open question. And for that, to answer such questions, not only of the fate of the information, but also related to the black hole entropy, you can see that one way to try to address those questions is to better understanding the role or the entanglement dynamics, the correlation dynamics, the processing of information, how is the information transmission, and the behavior of entropy in general covered spacetimes that may contain black holes. All those subjects are in the realm of the quantum information theory. However, quantum information theory only it's originally applied or originally developed in the context of non-relativistic quantum mechanics. So the idea is to try to generalize such concepts into general spacetimes and to general curved spacetimes and for relativistic settings, right? And what I'm going to focus more here is in the communication part, quantum communication. Okay? Quantum communication basically try to address this question here is to try to answer how much classical and quantum information. Classical information is bits, right? Quantum information are quantum states. They try to convey between two parts, and how much classical and quantum information can be conveyed between two or more parts when one uses a quantum communication channel. That is, if you encode our information in quantum system and send the quantum system between the two parts, right? That's quantum communication channel. And why that's interesting? Because in such scenarios, relativity can play a major role. Because in relativistic context, we can have non-trivial structures such as Cauchy horizons. We can have event horizons of black holes. We can have cosmological horizons due to the expansion of the universe. And we can have causal horizons due to relative motion of observers conveying the communication. So we have non-trivial structures which change the causal relation between the sender and the emitter, and this can change drastically how we can communicate in these scenarios. So to analyze quantum information theory in such a general spacetimes, and in a relativistic consistent way, we need quantum field theory, and in particular, quantum field theory in curved spacetime in order to describe general spacetimes and general gravitational fields, right? And what is that? It's basically, we are in a regime where gravity can be treated classically, as in general relativity. This way, gravity is described by a curved spacetime, classical curved spacetime, in which we have quantum fields, for instance, a scalar field here, but can be any field, which propagates through spacetime. We quantize it using the usual laws of quantum mechanics. We promote the field to an operator, satisfying the canonical commutation relations. And of course, the field in a given state has energy momentum, so we can backreact and curve the spacetime, which I'll put in a very pictorial manner this way. This is the semi-classical Einstein equation. The validity of semi-classical Einstein equation is a subtle matter. George has discussed a little bit about it in his talk. So I'm using it as just a schematic way to say, the fields change the space-time also, right? He backreacts on the space-time. However, when we do such quantization procedure of the field in curved space-time, contrary to what happens in Minkowski spacetime, where we have Poincare symmetry, which picks up a single a preferred vacuum state and associated with it a preferred particle notion. In general curved spacetime, there is no such symmetries. Hence, we have many vacuum states, infinitely many vacuum states, and particle concepts when we can define it, and none of them are preferable. The exception is when we have symmetries, and in particular time-like symmetries, time translational symmetries. So whenever we have a space-time with a time translation symmetry, we can pick out annihilation creation operators to define a Fock space, pick up a vacuum state, and define particles states associated with such time translation. The paradigmatic example is Minkowski spacetime, where the inertial observers defines a time translation symmetry for the spacetime. Hence, we can define annihilation creation operators, a vacuum state, which is the Minkowski vacuum, is the absence of particles as seen by inertial observers, which could measure the field to be at 0 temperature, right? However, even in Minkowski spacetime, you have another time-like translational symmetry, given, for instance, by the uniform accelerator observers, both in this region 1 and 2. This time translation are described by these hyperbolas here, in both sides here, that we call the Rinder wedge, regions 1 and 2. And these time translation symmetries enable us to pick a different set of annihilation creator operators, a different notion of vacuum and particles associated with it. And in particular, if you write the vacuum state of inertial observers as seen by the particle content defined by the accelerator observers, for instance, if we restrict ourselves to observers in region 1 here, okay, we see that the Minkowski vacuum state is actually, for those observers in region 1, accelerator observers in region 1, will be a mixed state, in fact, a thermal state, whose temperature is proportional to the proper acceleration A of the observers. Right? This is basically what we now call the Unruh effect, which states that uniform accelerating observers in Minkowski spacetime, in the Minkowski vacuum, experiencing a thermal bath of elementary particles at a temperature proportional to their proper acceleration, vindicating Steve's fooling previous discovery of that the particles concept is observer dependent in quantum field theory. Right? And usually, by using quantum field theory in curved spacetime, people have analyzed, for instance, the quantum communication process, but only in a limited setup, which is they consider specific spacetimes where we have at least two of those time translation symmetries. For instance, Minkowski spacetime. We can have also some other spacetimes like Schwarzschild spacetime can do a similar thing, so on and so forth. And in such limited conditions where you have two different notions of particles, two different notions of congruence, global congruence of observers, we can discuss a little bit about the quantum communication between those global sets of observers. But that was a very limited way to describe this process. So the idea was try to develop a way to discuss some how can communication process occurs in more general setup. So the idea was to try to develop a setup where we can answer some general questions about how much information can be conveyed between observers, but in a much more general setting, so in such a way that it would be valid for arbitrary globally hyperbolic spacetimes. We're going to use the quantum field as our communication channel. We're going to encode the information in the quantum field and use it to transmit information, but without the need to choose a particle concept. As we have a general spacetime, there is no preferred notion of particles. So we don't have to choose a notion of vacuum and particle states, and also in a way that both sender and receiver can move arbitrarily, can have an arbitrary motion in such spacetime, and can interact with the field only in the vicinity of their respective word lines, which is what happens in real laboratory experiments. We only interact with the field in the vicinity of spacetime. We don't have a global congruence of observers communicate. We have local observers communicating in their local laboratories, right? So that's the basic idea. So what we have is the following. We have a quantum scalar field phi in a general global hyperbolic spacetime. We have a sender which moves along a general word line, and it possesses a two-level quantum system which he encodes the information, Alice, the sender, encodes the information in his two-level quantum system. It interacts with the field for a finite amount of proper time to encode this, to imprint this information in the quantum field. This information travels through the field, and Bob, which also has a two-level quantum system, now interact with the field in order to extract the information encoded by Alice in it. So that's basically the process. So we have the system described by this Hamiltonian. This is the Hamiltonian of, it's not working properly. H phi is the Hamiltonian of the field. H int is the interaction Hamiltonian between each qubit with the field. So J can be A or B for Alice and Bob. Epsilon is the coupling constant of each qubit with the field, which we turn on and off in a finite time. This psi basically gives the interaction range of each qubit with the field. So it can be a delta function around the word line if the if the interaction is point-like, or it can have a decay described by some function psi. Phi is the field, the quantum field, and Z is basically the two-level degrees of freedom of the qubits, right? So the evolution operator of the whole system, 2 qubits plus fields, given then by this expression, which can be computed exactly and non-perturbatively, and yields this relation here. So we have a local interaction between qubit A and the field, a local interaction between qubit B and the field, and basically interaction between the 2 qubits mediated by the field in a causal manner. So here, f is a function, fa and fb is fa is a function that describes the properties of qubit A, fb describes the properties of qubit B, because basically it has the information about the coupling constant and the range of interaction of each qubit with the field. This phi of phi is basically this mirroring of the field with each of those functions. Delta is the commutator, basically, of the field, right? And delta of f, a, and b is this mirroring of the commutator with the functions. And E of f is this function here. Okay. And the most important is that you see that this interaction, effective interaction between the 2 qubits is causal because of the commutator. So what we're going to do is Alice encodes the information in her initial qubit here. Then we evolve the whole system. Bob is in the initial state rho minus infinity, with ready to measure state, so speaking. We evolve the whole system unitarily. And then at the end, we need to know what's the state that Bob will measure for his qubit. So what we're going to do is we evolve the system unitarily, and at the end we trace out that Alice and the fields degrees of freedom in order to describe the states that Bob's will measure here. And this will basically describes a quantum map which, given the initial state that Bob's codified the information, give us the final state rho B of Bob's qubit, in which he will extract the information sent by us. And this map, effective map between Alice's states, initial states, and Bob's final states is given by this expression. And the important thing here is this delta, which describes this communication channel in a causal manner because of the commutator of the field. So what we have is now a communication process which can be applied to general spacetimes with emission and sender in arbitrary motions in general curved spacetime, using the quantum field as a communication channel. So now we can address the question of how much information can be, classical and quantum information can be conveyed between the sender and the emitter, right? So to answer now how much information, what we basically do is compute what is called capacity of the quantum channel, E, right? Classical capacity gives us how much classical bits, how much classical information can be transmitted between the parts, and the quantum capacity gives us how much quantum information, that is, quantum states, can be reliably transmitted from sender to receiver. So the idea, I'm not entering the details here, but the idea is that what are those capacities? They are basically describing, for in the classical case, for instance, Alice wants to send a measured M to Bob, and the idea is that she wants to send the larger quantity of bits each time she uses the channel to Bob in order to optimize the information transmission. So how many bits she can transmit to Bob each time she uses the channel in a way that the error probability in the receiver's end is arbitrarily small, this gives what we call classical capacity. So the classical capacity of the channel is basically the maximum amount of bits that Alice can send to Bob in each way, in a manner that Bob can codify the message with arbitrarily small error probability, so they can communicate reliably in this sense. Right? So it's basically the maximum amount of classical bits that can be sent each time the Alice uses the channel and try to convey information to Bob. Such capacity, such number of classical bits that can be used per each time the channel is used, can be written in terms of the quantum channel, the mathematical form of the quantum channel, using the so-called whole-level Westmoreland theorem. It's this chi here is what we call the whole-level quantity of the channel E, and it's calculated using the von Neumann entropy and the specific form of the channel. And this is a very intractable expression. It usually cannot be computed for general channels. Fortunately, for this channel we have used, it has a very nice additivity process here, which is this process, this property here, which enables us to compute exactly that limiter of the product tensor of the channels, and yields this expression here, which manageable, can be computed, and we have done it, yields this expression here. So this gives the maximum amount of information that Alice can send to Bob, classical information, classical bits that Alice can send to Bob. H is basically the entropy, the classical entropy of a variable x, right? And we have now this expression, which shows that Alice and Bob can communicate at this rate. They can send classical bits to each other at this rate. And the most important, it's completely causal, due to this delta here. So whenever Alice and Bob try to communicate in causally connected regions, it's impossible for them to communicate. No matter how entangled is the field state, how complex is the field state, the motion of the observers, it's simply impossible for them to convey any information. We can also do it for quantum state, how much quantum states can be transmitted between the parts. For this specific channel, due to the interaction we have chosen, the amount of quantum information in this case is 0. They can only transmit class information, but not quantum information using this channel. However, if Alice and Bob, they have initially some entanglement they can share in their qubits, the situation changed a little bit. But this is what we call the entanglement-assisted quantum capacitance, which states that if Alice and Bob have initial entanglement between them, they can use the so-called teleportation protocol to transmit quantum information between them using this prior entanglement. So what is teleportation? Basically, Alice and Bob have an entangled state, which we described by this pair here. And by sending two classical bits of information, so Alice phones to Bob and transmit to Bob two classical bits of information, they use their prior entanglement, and now they are able to transmit a quantum state from Alice to Bob. So they can transmit a quantum state by using entanglement, their prior entanglement, and classical communication. That's basically the teleportation protocol. We can do the reverse also, which is called super dense coding, which now Alice and Bob have an entangled state, And now by transmitting only one qubit, only one quantum state, they can communicate 2 bits of classical information. So by using a quantum state and transmitting 1 qubit, they can convey 2 bits of classical information. But for those 2 protocols to work, they need to have some prior entanglement between their qubits. So using a generalization of such protocols to this general case, we can show that now the classical capacitor, that is, how much classical information they can convey to each other with assisted prior entanglement is basically the same as without any entanglement, which is given by this expression here. However, now, if they have some prior entanglement, they can convey, using this relativistic channel, quantum states to each other at a rate which is half the classical rate. But, and the most importantly, they can do it in a completely causal manner. And doesn't matter how much prior entanglement they have, how much entangled is the field state between the parts where Alice and Bob are communicate, it's impossible for them to communicate classical and quantum information in causally connected regions. Okay, so we can also generalize this. We did it in this recent work with my PhD students, Ian Barcelos, my former PhD student, Ian Barcelos. And we can generalize this for more parts. For instance, the so-called quantum broadcast channel we have published recently, where we have one observer try to send information to 2 other observers. Due to timing constraints, I won't be detailing this case here, but we can compute how much information the Alice can send to Bob and Charlie, B and C, and both in the classical and quantum case. And most importantly, again, everything due to those deltas here of the commutator of the field, everything is causal. So it's impossible to communicate in causal connected regions. We can also do it for the so-called quantum multiple access channel, where now 2 observers try to communicate with a common 3rd observer. And again, you can compute how much information, classical and quantum information, they can communicate, and everything is causal also here. We are just finishing writing the manuscript to submit it for publication. So what I want to talk in these final minutes is another question we're trying and still are considering, is which is about the energy cost for conveying information. Right? How much energy is necessary to convey information between parts? And in particular, if you have already our qubits, there is any extra energy needed in order to do the communication process. So we can answer this question. We did it again, me and my PhD student, Jan. I have done it in this work here in a very general context of asymptotically flat space-time. So any asymptotically flat space-time which may possess a black hole horizon, we can answer this question here. So by using this mode of communication, this general global hyperbolic but asymptotically flat space-time, we can answer or begin to answer this question of how much energy, what's the energy cost for conveying information. And the idea is very interesting because we use this, what is so-called no-surface quantization in order to be able to calculate it in these very general setups. The idea here is not, I'm not going to enter into details, but if you have a no surface in your space-time, in which the matter can be put in this form here, we can define quantum fields on this horizon, on this no surface, here, which satisfies the usual commutation relations. And with those quantum fields, we can define observables in the horizon, stretch energy tensor, for instance, on other observables, define quantum states, and so on and so forth. This is just, for now, is just a mathematical construction. There's nothing physical about it. The physics appears when one considers this no surface in our spacetime, right? So, for instance, so you have asymptotically flat spacetimes with a black hole horizon H here. So we have the asymptotic infinities, the square plus. We have our black hole horizon H there. The union of these two no surface will be our no surface, which we apply this construction. And if our field satisfies these two properties here, BB1 and BB2, which states that given the value of the field in the space-time, it extends uniquely to values on the horizon H and on the square plus. So they have well-defined initial values on square plus and the horizon, unique initial values. And this second property states that the Klein-Gordon inner product of solutions of the field equation in the space-time, the physical space-time, can be written in terms of Klein-Gordon inner products on the horizon and on square plus. If these two properties are satisfied, we can, for each quantum observable in the space-time, relate it uniquely to an observable in the horizon and infinity, and given a state, a quantum state for the field in the space-time, we can define a quantum state in this horizon and infinity construction. And that is interesting because even if the space-time possesses no symmetries, those no surface have some symmetries, in particular time translation symmetries and dilations symmetries, which can be used to analyze the problem in a very simpler and richer way. So what we have done here using this formalism is to analyze how is the expectation value of the total Hamiltonian, the total energy of our system, changes when we go from past infinity to future infinity, from this initial state before the communication process to a final time after the communication process has ended. So we can compute it, and we can split this variation of energy in basically three terms. The first one is the W phi. It's basically how the field energy changes, and it basically gives the energy from particle creation due to the change of space-time geometry. Right? Those second terms, which is the sum of WA and WB, gives this local term, it's basically the energy necessary to create our qubits, to turn them on and off, turn the interaction on and off of them with the field. We can estimate the value, for instance, consider an inertial qubit point in Minkowski space-time interacting with the field in a point-like manner, right? So we turn it on, we turn the interaction on in a time scale given by the inverse of this alpha A, keep our qubits turned on for some time, proper time, then we turn it off again in a time scale given by the inverse of this alpha here. We can compute this energy cost, and basically it yields this first expression that W is proportional to alpha, or put in another way, the energy needed to turn on and off the interaction times the time scale needed to turn it on and off satisfies this relation here, which the usual interplay between energy and time we would expect. And finally, the third term, WAB, is the actual energy if we try to communicate. So these first two terms, they appear independently if we're trying to communicate and communicate or not. They are always there once we have created our qubits. However, if you are trying to communicate, you have this third term here, which is the communication contribution, which can be shown to yield exactly 0 for our channel. So there is no extra cost in communicating. If you have already created our qubits, you have energy cost for that, but there is not an extra energy cost needed for the communication process itself. So that's the basic idea. And now we're trying to analyze further this energy costs and in context related to the entropy bounds and the flow of energy in order to give a more deep insight on this relation between how much energy is needed to convey information, and then apply this to cases of the evaporation of black holes and such things. So that's, I'm going to end it here. Thank you very much again.
Questions?
I don't know if you mentioned it, but do you consider, like, you're moving information across space-time, do you take into account possible decoherence effects? And you have horizons, or also have you taken into account possible entanglement degradation effects that Roberts works on?
No, the decoherence naturally appears due to the interaction between the qubits and the quantum field. So they are naturally present here, and that's why basically this map is not unitary, right? So
this map is not what?
Unitary. This E map is not a unitary map. The decoherence due to horizons, we are not considering the back reaction on the space-time, so not consider the gravitons, degrees of freedom, which would further, which give this another effect of decoherence due to the horizon. Decoherence due to the horizon. So that we have not considered here.
Okay, thank you.
Other questions? Okay, let's thank the speaker again.
Thank you.
And we meet here again at 11 sharp. We're a bit late.